Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on July 30th, 2025. So published just 2 days ago. This paper introduces a new training method that helps a 7 billion parameter model achieve an 83.6% success rate on a really tough set of unseen tasks. The paper is titled RLVMR, Reinforcement Learning with Verifiable Meta-Reasoning Rewards for Robust Long-Horizon Agents. And the way they achieve this is by getting the AI to think about its own thinking process. It tackles a key problem where agents learn to solve tasks through flawed logic, and it fixes this by directly rewarding good reasoning steps, not just the final outcome. And it seems the community is really picking up on this idea. Looking at the reactions on X, the conversation really hones in on that central question of whether agents are truly reasoning or just finding lucky shortcuts. One of the paper's authors posed that exact question when sharing the work, and that post is getting strong engagement with over 100 reposts. Others are echoing this, describing the method as a way to train AI without making it dumb, by rewarding the quality of the reasoning process itself to create more robust agents. Alright, and these first charts really visualize that exact point about creating more robust agents. They compare the new method, reinforcement learning with verifiable meta-reasoning rewards, against both a standard training method called GRPO, which only rewards final success, and a basic vanilla model. Looking at the results on the ALF World benchmark, the chart on the left shows a huge jump in success rates, especially on new, unseen tasks. And the chart on the right really shows us why. This new method drastically cuts down on how often the agent gets stuck in loops, what's called the repetitive action rate. And this next figure gives us a great conceptual diagram of how they pull this off. On the left, you see the standard approach, where an agent tries a sequence of actions and only gets rewarded at the very end if it succeeds. This can accidentally reinforce flawed logic that just happened to work. But on the right, with the new method, the agent first states its intention, using what's called a meta-reasoning tag, like planning or exploring, and then acts. It gets immediate, step-by-step feedback on whether that reasoning was good. This process-level supervision is what stops the agent from getting stuck and builds a more robust problem-solving ability. So this next figure breaks down the technical framework for how that process-level supervision actually works. It's a two-phase process. First, in what's called a cold start phase, they annotate expert solutions with those meta-reasoning tags, like planning or exploring. The agent then learns to produce these tags through supervised fine-tuning. After that, in the main reinforcement learning phase, the agent tries to solve problems on its own. The key is that its rewards are based on both the final outcome and on the quality of its reasoning within each tagged group. Alright, moving to the results. This table really puts the numbers to the test. It compares performance on two challenging benchmarks, ALF World and Science World, across different difficulty levels. L0 is for tasks the agent has seen, L1 is for new variations, and L2 is for completely new tasks, and the results are just striking. The new method, reinforcement learning with verifiable meta-reasoning rewards, consistently comes out on top. With the QN7B model, it hits an incredible 83.6% success rate on the hardest unseen tasks, a huge jump over the next best approach. Building on those high success rates, this next table then details another key aspect, efficiency. It shows the average number of actions an agent takes to solve a task, where a lower number is obviously better. And across both the ALF World and Science World benchmarks, the agent trained with reinforcement learning with verifiable meta-reasoning rewards is consistently more direct. On the hardest unseen ALF World tasks, for example, it needs only about 15 actions on average, a nearly 30% reduction from the GRPO baseline. This efficiency gain directly addresses that inefficient exploration problem we discussed. Okay, so to really understand what makes this system work, the authors perform what's called an ablation study, where they take the system apart piece by piece to see how important each component is. This table shows the results on the hardest unseen tasks, and it's clear that every part is critical. If you remove the final outcome reward, performance collapses. But removing the meta-reasoning reward, that step-by-step feedback, also causes a huge drop in success. This really proves their main point. You need both the process and the outcome to train truly capable agents. So, to wrap things up, the key takeaway here is that how you reward an agent matters just as much as what you reward it for. By shifting focus from just the final success to also rewarding the quality of the reasoning process itself, This method builds agents that are dramatically more robust and efficient. That's it for this episode.